You're enjoying viewer-supported television, channels 45 and 49.
How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, again, still. And my principal business is physics. And today, a program which I entitle Some Extraordinary Adventures. Some Extraordinary Adventures. Consider the following, and some of the results you will hardly believe. I have here a flask with some water in it, and I have applied some heat from below, and the water is boiling. We say the water is boiling when the vapor pressure given off by the water, delivered by the water, is equal to the atmospheric pressure on it. Now I am going to remove that boiling flask to a cold tripod, and I'm going to shut off my gas burner, shut off the gas, and I have put this tightly stoppered on this cold tripod, and you see an astonishing thing. Well, somebody says, what's astonishing? The water stopped boiling pretty nearly. Yep, the water stopped boiling pretty nearly. It'll stop altogether pretty soon. And I have it tightly stoppered. Now what am I going to do? From time to time, I'm going to lay my hands, which are colder, of course, at a lower temperature than that flask. I'm going to lay my hands on there, and the water will boil. Now, because it's too hot for my hands, I'm wetting my hands a little bit in some ice water. Now, watch, 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 watch. Oh, yes, notice the laying on of hands. I have boiled the water. Now you must give me your undivided attention to another matter. You see, I am boiling water there by applying heat. But over here I have another demonstration where I'm going to boil water not by applying heat, but by taking heat energy away, and I'm going to boil the water so fast that it's going to get so cold by evaporation that it freezes. Now, who'd believe that? So here's what I have. I'm going to take a little watch glass in which I put a little water, and I'm going to put a bell jar on top of that, on a pump plate which has a hole in it, and I'm going to take out some of the air from here with a vacuum pump. Pump, 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 pumping out. So the pressure in here gets less and less and less. Now, less and less pressure in here means that the water in here can evaporate more and more and more readily. Now, you know evaporation is a cooling process. So as the water evaporates, it is cooling down. Its temperature is getting less. But pretty soon, the vapor pressure of the water will be equal to the pressure in the bell jar, which is very low. And so at this time in our affairs, we say the water is boiling. But remember, I've applied no heat to it. It's boiling because I reduced the pressure and let it evaporate so that the vapor pressure is equal to the pressure in the bell jar. Now it is boiling. Now it is boiling without the application of heat. But it's boiling in such a manner that it is losing its heat energy because I'm not applying any. And what do you suppose will happen? It may, I hope, if things work, if I have tight enough vacuum, it will freeze. So I'm going to freeze the water in this little watch glass by boiling it. More than that, I should add a phrase. I have below, in the setup, in my apparatus, a little vessel of concentrated sulfuric acid, because concentrated sulfuric acid is hydro something. It takes up water vapor. So the water vapor that comes off here goes in there. Now, do you notice how I attacked this matter? I said it's hydro something. So here is a good idea for looking up words and adding to your vocabulary. This contributes nothing to my experiment. So I'm going to go to this. But before that, has not the water here ceased boiling? Now watch me lay on my hands again. Watch me. And I say the laying on of hands is a mysterious thing. Watch it. Oh, there it goes. There it's boiling again. Now, if we can get the camera tightly on the little watch glass in my chamber here, very tightly, so that we see the water in the watch glass. There we are. Now I'm going to start the pump, and we will silently pray for the success of this. Watch it now. First, you see it clouded up a little because of an instantaneous reduction in pressure. Stay right on the water. Now I see some occluded gases which are locked up in the water, leaving the water. They are gathering there in little bubbles. In little bubbles. Now the water is beginning to boil. Now the water is beginning to boil. And I'm tightening the bell jar. Now, let us hope. The water is boiling. The water is boiling rapidly. And it takes a couple minutes or 3, depending upon how good a pump we have. The water is still boiling viciously. On occasion, some gases locked up get released and flip, they go. Watch closely. This takes a little time. This takes a little time. Now things are quiet. All the gases locked up in the water have fled away because of the reduction in pressure. Oh, there was a little there. The water now is very cold because it is evaporating at very low pressure. One needs to have patience for this experiment. There it is! There it is! I say we have ice! Oh, man alive! Let me shut this off. Let me take this out. I want to show you that I've got ice. I want to show you that I've got ice. There it is. Now, ladies and gentlemen, just look at that. That's ice. That's ice. How do I show it? There it is. There's a piece of, that's pretty. That is ice. And I say, this is fantastic. And if anyone has any other view, he is lifeless and dead. This is absolutely enchanting. So what did I do? I froze water by boiling it at lower and lower pressure, at lower and lower temperature, which bears on the following. You go to the top of Pikes Peak. You can wash your hands in boiling water. Why? The atmospheric pressure is so low, the boiling temperature is very low. The vapor pressure of the water need be very low in order to equal the pressure of the atmosphere on it. You can't cook beets in an open pot less than 2 hours, if then. And as for brewing tea, the water hardly gets ever hot enough to take the juices out of the tea leaves. Now, let's get back here. But before, I suppose, ladies and gentlemen, I have done this experiment 10,000 times in 50 years. And I am repeatedly enchanted by this adventure. Look at that. Oh, the ice is gone. It's melted. But is this not a dramatic adventure? Let's go back. Do you see the water in this chamber is absolutely silent, lifeless, dead, and quiet? And I am going to lay on my hands. Watch it. A little cold water. Watch it. You say the right abracadabra, the right hocus pocus, in Hindustani or Swahili, boil. Ah, there it's boiling. Ah, man alive, that's something. That's something. Now, how long can I continue to boil that water? Oh, about an hour. About an hour. Well, let's go on. Some exciting adventures. I have another exciting adventure. Notice, people. Let's get back here to my experiment on the freezing of water by boiling. You remember I said I had a little sulfuric acid in this lower chamber, which is right there. Now, some of the water vapor went into the sulfuric acid. And what is the interaction of water with an acid? Answer, exothermic, meaning that heat is evolved. So, if you give me your attention here closely, if I feel this chamber now of acid into which some water vapor has gone, I would feel it what? Answer, I would feel it hot. And so closeth the adventure, magnificent to witness. Here is another one that's wonderful. I have here some ice cubes in a glass of water. Some ice cubes. I have here a string, and my problem is to get out, so I'm wetting that string a little bit in another dish, so it takes on a little rigidity and weight. I wish to get out some of the ice from that glass of water by a strange and uncommon device. Watch me. Watch me closely. I want to get out some of the ice from this vessel. How can I do it? Can't wrap the string around. I'm not allowed too many accessories, but I am allowed one, and here it is. Salt in a salt shaker. I'm going to put some salt on there, and I'm going to wait a moment, and now you know a strange thing happens. A very strange thing happens. What happens? The salt depresses the freezing point. Some of the ice is melted by the salt, whereupon water arises, so the string finds itself embedded in a little puddle of water on a hunk of ice. But because there's lots more ice than there is water right there, the water that resulted from the melting ice now freezes, and the string is fixed to it. We hope. Watch it. Watch it. Watch it. Watch it. Watch it carefully. There it is. I have lifted some ice out, and that is a wonderful adventure. Indeed, have I not called this program Some Remarkable and Extraordinary Adventures in the Subject of Heat? Incredible. Incredible. Oh, let me try it once more. The water is silent and quiet and still. Not any evidence of boiling. I'm going to lay on my hands again. Watch it. Watch it. Boil, my dear, and it boileth. Thus readeth the scriptural lesson regarding the boiling of water. And would you not agree, ladies and gentlemen, that these investigations have uncommon beauty and drama, enough to stir the deadest soul? And I thank you for watching. How do you do, ladies and gentlemen, and boys and girls and teachers? I'm Julius Sumner Miller, and physics is my business. And my program today I entitle Some Miscellaneous and Wondrous Adventures in the Subject of Heat. Now, before I leave it, here is an interesting inquiry for you to pursue. I mentioned on an earlier occasion the behavior of this little radiometer, known as a Crookes radiometer. And I said that the way it's devised and designed and the way it works is that the black faces always retreat from the observer. Question, what would this do if placed between two cakes of ice? Supposing I placed it between two cakes of ice, what would it do? That's a very good question. But let me go on with my adventures. Here I have a large tin can in which I have put some water, and I have boiled the water for a while and driven out all the air and the occluded gases in the water. And now I'm going to, and you see that because the steam here, which is condensed water vapor, now I'm going to take this away from the burner, and I'm going to stopper it up, and I'm going to shut off my gas here. And I invite you to listen. Oh, listen, listen, listen. Oh, man, something is happening. Now, you know all about this. The water vapor inside is condensing into the water liquid state. The pressure in the can is getting less, and the atmosphere is beginning to do its... Oh, there it is. But I don't want to wait all week for it. I'll just hasten the process. Watch it. Oh, watch it. There it is. Oh, there it is. It got me on the side a little bit, but that's all right. This is an experiment in physics. Isn't that incredible to witness? Fantastic. Now, more about this. Supposing I tried to take out that stopper. Supposing I tried to take out that stopper. Answer, it is very difficult to get out. Why? Because the pressure in the can is vastly less than atmospheric. But there it is. I'm going to do something stranger still. I'm going to pour some more cold water on there. No, I was hoping to hear the water in there boil again, reducing the pressure. I think I can do that. I want to do that. Yeah, I hear the water boiling. But let me go on with my business. Miscellaneous adventures. Here I have a cake of dry ice. Now, you know what dry ice is. Solid carbon dioxide. Solid CO2, a gas made solid. Has very strange properties. It sublimes. That is, it disappears without ever going into the liquid state, like camphor. Here I have a silver coin, a silver dollar. I'm going to lodge it in here and watch. I am melting some of the... Watch it. Oh, a little troublesome. There we are. Come on. I'm having a little trouble with it. I want to warm this coin up. Notice conduction. The heat of my hand going into the coin. I'll try it once more. There we are. Here we are. Listen. Yeah, this is to be likened to a thing in the history of physics known as a Trevelyan rocker, which a Britisher of long ago designed, and I invite you to go look into it. Trevelyan rocker. Now, look at that. I want to know why it's doing that. Look at that. And I'm going to tell you why it's doing it, because, you know, I'm kind-hearted. It makes contact on one side with the dry ice. The other side is left free. Heat energy is taken away. Gases arise. Push it over. I haven't said everything, but that's enough for you to think about. Miscellaneous further adventure. Question. I want to cook a hamburger very fast. Question, should I put the ground meat in a skillet, turn up the burners high, and cook it very fast to cook it fast? No. Answer no. Why? Here I have cooked a hamburger very fast, and it is all brown and black and scorched on the outside, but it is not cooked inside. Why? It is not cooked inside because carbon is a good insulator, and the meat didn't get cooked inside. So here is a hamburger that I have cooked very gently and slowly, and it is cooked entirely through and through. So, paradox. In order to cook a hamburger fast, you cook it slow. And I think that's wonderful. Next miscellaneous adventure. Housewives, teachers, people who sometimes prepare onions find that it makes them cry. The vapor pressure is very high. That's why you cry. Notice, vapor pressure very high. That's why you cry. I'm a poet and don't know it. Question, how can I make ready an onion so that when I peel it and slice it and dice it, I don't cry? Answer, put it in the refrigerator, in the freezing unit for a little while, and lower its temperature very substantially, as I have done with this one. It's a little hard to cut, but I smell nothing. Why? I have lowered the vapor pressure. Now, another discussion. Viscosity, another interesting thing. Viscosity, V-I-S-C-O-S-I-T-Y, viscosity. What do we mean by viscosity? We mean the freedom with which something flows. So you put crankcase oil in the crankcase of your car, and when it's cold, it does not flow so freely. When it gets warmer, it flows more freely. So in the case of liquids generally, the viscosity goes down the higher the temperature. And I have an interesting little tale to tell. Here is some molasses in this vessel. It is at room temperature. If I should pour it, it would pour so fast. Now here is some that I have cooled, chilled in the refrigerator. And clearly it would pour at a lesser rate, very much more slowly. So I have to tell you a story. When I was a little boy, my mother used to make cornbread, Johnny cake, using molasses. And she had a recipe all in her head, and the recipe called for the following. In the summer, the recipe called for 3 glubs. You got it? She turned over the jug and it went glub, glub, glub. And that was enough for the recipe. But in the winter, there was a different number of glubs. And I could never understand that when I was a little guy until I learned what we mean by viscosity and how it behaves with change in temperature. Question, did my mother have more glubs in the winter or less glubs in the recipe for her Johnny cake? I think that's a wonderful, good question. Next demonstration, strange one. Wonderful, miscellaneous adventures. Here I have a beaker, and here a hollow sphere in which I have some lead shot. So, this experiment has to be virtual, and it is a wonderful thing to witness. Watch me. We will imagine that I have some water in this beaker. Now, this sphere is so designed that if I put it in warm water, it sinks, and if I put it in cold water, it floats. That is warm water at room temperature, say, and cold water, that is ice water as you would drink water and ice. Now, here is a wonderful thing to do. Supposing I put this in a vessel of warm water and it sinks to the bottom, just as we have it here. Now, what could I do? I could add some ice. Add ice. You see, this experiment, ladies and gentlemen, is a virtual one, and you will imagine it. I add ice, and lo and behold, like a mystic business, up comes the sphere, because as the water cools, it gets more dense. On the other hand, supposing I put it in a vessel of ice and water of such composition and temperature that it just floated. Here it is just floating. Here it is just floating. Now, if I left it here in the studio, as time goes, would not the temperature of the water rise? Would not the water get less dense? And what would this do? Creep down ever so slowly. A very mystic adventure regarding the floating and sinking of a hollow sphere. So you see, people, how I entitle things. The mystic adventure, because it is something to think about, which is not generally in the books. Next demonstration. Wonderful thing. I spoke about the viscosity of liquids. The viscosity of liquids goes down with higher temperature. That is, the oil in your crankcase flows more freely, the hotter the system. But how about the viscosity of gases? The viscosity of gases. The viscosity of gases. It is a remarkable thing that the viscosity of gases increases with rise in temperature. And I have a demonstration which we will imagine. Here is a T-tube, unsymmetric. This arm is short and this one is long, and it's connected to a burner. And here's what I would do. There is the tube with unequal arms, and I put gas in here, and I light the ends of the tube which are turned upwards. I light the ends of the tube. The first thing we witness is this. This flame here would not be as high as this flame there. That's the first thing to observe, and that's very important. Why would we see that? Well, answer. The drop in this line is much greater than the drop in this line, so this is getting less gas than that. Now remember what I want to do. I want to show that the viscosity increases with temperature. So, with these two flames, this one low, that one high, I now play another flame on this pipe. This is a tube. I used to say a hollow tube, but it's a tube. You know, a tube's got a hole inside. Question. When I heat this, what happens? This flame goes out. And that's a remarkable thing because, obviously, when we heat the tube, the bore gets bigger, so more gas should come here. But more gas does not come here. It flows more sluggishly with the higher temperature. So it is a most uncommon thing to discover that although the viscosity of liquids goes down with rise in temperature, the viscosity of gases goes up. And now, once more, with my oscillating coin, there it is, there it is. And I think that's wonderful to see. I urge you, whenever you handle dry ice, CO2, be very careful. 95 degrees below 0 centigrade, enough to severely freeze you. And I thank you for listening. How do you do, ladies and gentlemen, and boys and girls, and teachers, and mothers and fathers, and people and parents? I'm Julius Sumner Miller, and physics is my business. And before we go further, this is a program on extraordinarily cold stuff. Indeed, it is so cold that I have something going here that we must get a look at. I have a tea kettle with some stuff in it boiling on a cake of ice. Oh, look at that. And my tea kettle is whistling. Isn't that something? So, question, what's in that tea kettle? I'm going to tell you, liquid nitrogen. So, as a point of departure, consider the following. Oh, by the way, let's get a view of what I've written here. Heat the air by talking. I made a little calculation. Somebody remarked that I did a lot of talking and the air got hot. So I thought I'd make a calculation of the same. It turns out that ordinary talk, such as I'm doing here and now, develops about 100 ergs of energy per second. That turns out to be about 1/10,000,000th of a watt. 1/10,000,000th of a watt. So it turns out that if 400 million people talked at once, they could light a 40-watt lamp, which goes to show you how much energy really comes out of this mechanism called talking. But regarding my program, the drama of real cold stuff, I have made a note or two. If we had ice alone, as we have here, that's 0 degrees centigrade. If we had ice and salt, a mixture, the best we can get is -20 degrees centigrade for ice and salt. If we put dry ice, here it is right here, dry ice, that solid CO2, with alcohol, a mixture of that, that would give us -78.5 degrees centigrade. So we're getting down in the world, you see. But what do I have here? I have some stuff called liquid nitrogen. Liquid nitrogen, and the temperature is -195 degrees centigrade. I tell you, people, that's real cold stuff, and I want to show you some dramatic experiments with it. First, here is a Frankfurter. Let me pour some of this stuff out so you'll see what it looks like. Watch it. Look at that. Look at the enormous vapor pressure. Vaporizes very quickly. I'm going to put a hot dog in here. Listen. Boiling very rapidly. Boiling, because the hot dog is so very hot for the stuff. Here I'm going to put an onion in. Now, you know if I cut that onion at room temperature, the vapor pressure, it'll smell, what shall I say, beautifully. I'm going to chill it in here. Chill it in here. Or consider the following. I have here a lead spring. Now you see how absolutely unflexible this lead spring is. Absolutely. No elasticity at all. I'm going to cool it in there. Listen, listen. Listen to it boil. Or consider a rubber ball. Watch. Rubber ball, fairly elastic. Fairly elastic, although rubber is inelastic. I'm going to put this rubber ball in there. Just let it cool off. Notice, making the stuff boil, increasing the vapor very, very much. Now, what do we wish to show? That the properties of things are enormously changed by reduction in pressure. Here is another beautiful illustration, while those other things are cooling off. By the way, notice again, my kettle is boiling on a cake of ice because the ice is hot for the stuff inside. And by the way, I invite your attention to the enormous frost gathered on this kettle. Why? Because the water vapor in this studio, in this classroom here, is very, very much, and it is condensing on that kettle. Here is a lead plate. Lead. Now, you know if I wanted to make music, I wouldn't have a lead plate. But listen. Thud. Dead, dead, dead. I am going to cool it off at a very low temperature, and it will have a remarkable property. It will sing like a steel plate. Or, consider the following. A balloon. I'm going to put a balloon in here. Cover that over. Let me get out my rubber ball. Watch. 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 I'm going to drop it on the floor in front. Watch it now. Watch it. There it is. There is that rubber ball. I want to do that again because that's a lot of fun. Oh. Now, give me your attention strictly. Here is that rubber balloon. Look at it. Look at it. Look at it. Look at it. The heat of my hand warming the gas, expanding the gas in the balloon. Now, why did the balloon get tiny, tiny, tiny? Because lower and lower temperature decreased the volume of the gas. This is Boyle's law. Now, let me go and fish out something. Notice, I dare not go in there with my bare hands. What did I put in there? Oh, there's the hot dog. Look at it. Look at it. That's the hot dog. Let me put a couple marshmallows in there. Let's get a few. Too bad to waste that, but it won't be wasted. I can eat it. The balloon again. Watch it. Very cold stuff. Now, what did I want to show you? Oh, the lead. The lead. Where did I put that? Oh, I guess Yeah, watch it. Watch it now. Watch it. Watch it. I'm going to put a weight on here. I'm going to put a weight on here. Notice. Notice. Notice how elastic it is. It has a little oscillation. I didn't cool it long enough. Now, where am I? Consider the following. I have here a copper tube and a steel tube. I have some liquid nitrogen in here. I'm going to submerge this system with a cork stopper into this Dewar flask, this thermos bottle. And what can I prove? Well, first you'll see an enormous stream of stuff emerge from here, but the water vapor will gather on here and freeze, and thus we can determine the thermal conductivity of metals by this device. Watch it now. Watch it. Look at that. Oh, that's terrific. That's terrific. Incredible. Now you watch the... Watch the frost gather. I'm coming back here. What did I put in here? I put in here another rubber ball. Notice, it was sort of elastic. Watch it. There it is, rubber ball. Now, where is that plate? Listen to the plate. I have to get my little mallet. Listen. You remember it was dead thud-like. Listen. Huh? I'm going to cool it some more. The strange properties. One thing more. I have here an electric lamp, as we call it, and I'm going to plug it into 110 volts. Watch. I'm going to plug it into 110 volts, and the lamp will light very feebly. There it is. I hope you can see it. Very feebly lighted. Now I have a coil, a wire coil in series with the lamp. I'm going to cool the coil. A long time ago, and another time later, I will show you that the electrical resistance of a conductor decreases with lower temperature. So, if I freeze this coil, watch the lamp. Watch the lamp. Is not the lamp getting brighter? The lamp is getting brighter. Brighter, brighter, brighter. Brighter and brighter. Look at the lead coil. Look at the lead coil. Look at the frost here, and this is a beautiful demonstration. Do you see the copper is frosted all the way, whereas the stainless steel is frosted only to here, which suggests that copper is a vastly better thermal conductor. Now, where am I? I like to look at that balloon again. Look at that. Look at that. It's a little cold on my hand. Little cold on my hand. Now, a tragedy to do. Here is that beautiful flower with which we opened the show, and I hate to abuse it in this way, but I want to show you the instantaneity with which this process of freezing takes place, which now has something to do with this new subject of cryonics, the freezing of human beings who have just now died, in the hope of preserving the cadaver, the body, for future resuscitation. when this is conceivably possible. Look how bright the lamp is now. Notice, very bright. The resistance of a conductor decreases. Watch the lamp now go dimmer. I'm going to immerse the rose in the liquid nitrogen. Watch it. Boiling vigorously. Boiling vigorously. Pretty soon, when it reaches the temperature of the liquid nitrogen, the system will cease boiling, and you'll see the dramatic effect that has taken place. One further thing, a little bell. Listen to the pitch. Now I'm going to freeze it. Notice it boiling? Watch the flower. There it is. A shameful thing really to do to so beautiful a living thing, but this is the consequence of very low temperatures. I want to try the lead plate again. Watch the lead plate. There is a ring. There is a ring to the lead plate. And as for those marshmallows, if I can get one out, watch it. There is the marshmallow. There it is. And now, what remains to be done? To point out to you that the lamp is dimmer now. Oh, my kettle is empty. And I can try one more pair. Here is aluminum and brass. Aluminum and brass. Let us see the results here. There it is. And we shall see the frost gather. And here is another ball. Watch it now. There it is. And finally, the balloon, whose volume is diminished nearly to zero, volume of gas. But the response to the thermal energy of my hand, very substantial and quick. And I say, the drama of low temperature stuff is something to be stirred by. And I thank you for listening. How do you do, ladies and gentlemen, and boys and girls, and mothers and fathers, and everybody? I'm Julius Sumner Miller, and physics is my business. And today, a strange kind of physics for an old man, an old physicist. The physics of toys. I don't suppose there is another physicist in all of history, dead or alive, who has played with them so abundantly as I, for the purpose of understanding why it is that it works. I'm reminded that the great James Clerk Maxwell, when a little boy, was given to the phrase, "What's the go of it?" Meaning, in my phrase, why is it so? Why does it do what it does? Or as Kepler used to say, why things are as they are and not otherwise. So I'm going to entertain us with some explorations into the physics of toys. I have characterized toys as mechanical toys, acoustic toys, thermal toys, magnetic toys, electrostatic toys, electric toys. I don't have any nuclear toys, but maybe in due course. So let's look at some at random. It does not matter what the order, but here is a mechanical toy which is very enchanting. I have here a little dog, which you recognize as Pluto. His legs are free in the plane of his long front to rear axis. And I have a string attached to his nose, and to the end of the string, some weights, paper clips. Now I put him on the table with the string hanging over and the paper weights hanging freely, and I'm going to put him into motion. Watch now. There he goes. Now I'm going to stop him because there is something to say. Does not reason suggest that when he gets to the end of the table, he should fall off, be pulled over? That is what reason suggests. But I'm going to show you this is not what a physicist expects, nor indeed is this what will happen. Watch it now. Watch it. Oh, notice a little too much friction there. I'll start him again. Watch him. No, he didn't fall over. And now I'm going to remark about the physics. Here in the horizontal, the pull was horizontal. So a horizontal pull can produce horizontal motion. Now when he gets to the very edge, I hope you see that the pull is vertical. And the vertical pull has, as we say in physics, no component in the horizontal, so he cannot move further. Indeed, here is a pair of firemen, identically equipped, and watch. One would think that they would fall over. No, they didn't fall over. And I am reminded, doing a program on the physics of toys in Oslo, Norway, I decided to have a wager with the professor who is playing the game with me, and so we will race these two. Watch it. Watch it. Oh, Disney would be delighted that his Pluto won the race. There we are. So, what am I led here to say, here and now? The competence of children is shamefully underrated. I could teach the physics of this to 4-year-olds, indeed 2.5-year-olds. I gave a lecture to about 100 pre-kindergarten, kindergarten children in Australia last year. Very exciting they were. All right, next demonstration. Next demonstration. I have a little toy car with a smokestack and wheels, and I'm going to turn a screw thing here. What am I doing? I am winding up a spring. I am storing some elastic energy in a wound-up spring. Then when I release the spring unwinds, turns a fan, blows a stream of air out of this smokestack. Watch it. Now I'm going to show you something very dramatic. Why does the ball stay there? Well, everybody says, Professor, there's nothing to that. The stream of air coming out of that stack is vertically up. The air pushes up, the ball pushes down. When they are equal, the ball stays there. And that would be right. But now, supposing I turn that smokestack off the vertical, and the ball still stays there. Aha, we got a new piece of business. And that ain't so easy to understand. Somebody says, well, Professor, that ain't so easy. That's not good English. Well, I take liberty and license with the language. Notice, liberty and license with the language. That's very good alliteration. Watch this now. Watch it. And the ball is spinning. And the ball is spinning. Of course, too much off the vertical, fall down. And I want to know why it does that. Oh, this would take me about an hour of blackboard mathematics to show you why. But let me say this. Why the ball stays there in this position, spinning in a very interesting way, which you witnessed, is quite lies in the same category as the following. Why I can throw a baseball in a curve, why an airplane can fly, why a smokestack has a good draft, why a bird can soar in the air, why a flag can flutter, and 1,000 such things. So you see the physics in this toy car is not trivial. Not trivial. Consider the following. Notice, these are mechanical toys. Here is a little propeller and it has three blades, and they are pitched in a very certain way. Now I have wound up, oh, that one is wound. Let me take, there. Whoop. What am I doing? Oh, there's a little trouble with that spring. I have stored some twist energy in a spring. When I release it, it will unwind, and that propeller is going to go up. Why? The blade is pitched. So as the whole wheel turns, the blade grabs some air, as we would say, and pushes the air down, and that's why it goes up. So a bird can fly only because he pushes the air down and he goes up. Conservation of momentum, we call it. Watch it. There it is. And of course, there I have a spinning top, which I could talk about for an hour. Let me do another one. Oh, watch it now. Watch it. Oh, way up, and there it comes. And we have a spinning top on the floor, which perhaps can be caught by the camera, and that's so. Very good, men. Okay, mechanical toys. Another one. Here is a wonderful one. I don't like to play much with weapons of war, so you have once detected my philosophy, but this is rather harmless. Here is a hollow chamber in the shape of a gun. The chamber is, as one would say now, empty. Oh, no. It's filled with air. And here is a ping pong ball. And I put the ball in there. And now I squeeze suddenly on here, and the ball emerges. Indeed, I have made a very profound experiment out of this. If I shoot this ball at some angle with the horizontal, and then at another angle with the horizontal, and then at another angle with the horizontal, I find very nearly the following, and this is quite amazing. If one shot a projectile like that and it took this flight, the question is, when would you expect maximum range? Well, theoretically, maximum range is at 45 degrees. And so we can show that with this toy. Now, there is another interesting problem. Galileo showed that if there is a target intermediate in here somewhere, that target can be hit by this weapon by two routes. One that goes like this, and one that goes like this. And they have very interesting properties. This smaller one is as much smaller than 45 degrees as this one is bigger than 45, which is a very exciting thing. And Galileo did this in the 16th century. So you see, people, that playing with a toy, this may be for child's play, but the physics ceases to be child's play. It can be very substantial business. Let me show you another one. Here I have my monocyclist. Mono, one, cycle, wheel. Monocyclist. Here I have a string, one end of which is fixed to a support there. Now you know that if I put this monocyclist on the string, the center of gravity of the cyclist is far above the point of support, whereupon, as we say, the system is unstable. Unstable. Very certainly will tip. I wish to do two things. I want to make him more stable. How can I do that? I can do that as follows. I can load his arms with a stick and a heavy weight. Here's the weight, a lead weight. Put such in each arm. Notice I'm getting a little entangled here. Put one in each arm. I'll go get my string again. And now let me discuss the physics briefly. Mark you people, I am giving only the most superficial inquiry into the matter. Each one of these toys could have 100 pages of mathematical physics written on it. So I am disposing of it quite in a trivial way. What have I done? I have lowered his center of gravity below the point of support, and I have also increased what we call his moment of inertia. I have made his mass far out from his central axis. And now we hope he can ride with absolute immunity. Watch him. There he goes. And there he comes back. And there he goes. And there he comes back. And the faster he goes, the more stable, which is because the wheel has a certain gyroscopic property, which I have no time to engage in here. So the monocyclist lowered the center of gravity below the point of support and increased the moment of inertia. Let me say a word more about that. Supposing I'm an ice skater, skating, and I stop with one leg up and both arms out, and I spin at a certain speed, pirouetting. My mass is far distributed from my axis of rotation. Now I drop my arms. My moment of inertia becomes less, and my angular velocity very much more. Or, consider finally another. Here is a little dog with a flexible neck, and I push his nose down into some stickum stuff. I push his nose down. Watch now. Watch. Watch it. Watch him. Come on, come on, come on. Oh, come on, you rascal. He stuck him too much. Oh, well, notice. What I wanted to show you is that he rotates about his center of gravity and would land on his feet. And thus I have explored in a trivial way the wonderful adventures in the physics of toys. And I thank you for watching.
Thanks for watching.
How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business, and more especially now the physics of toys. And as you might guess, it is filled with enchantment for me. So, our first program, already done, I devoted to the physics of mechanical toys, mechanical. Let me now explore a little with you some toys that have acoustic mechanism and thermal mechanism, acoustic. Let me go back to one I did before. I talked about the mechanical properties of a toy gun, where we can determine the range, the maximum range, and such other properties of projectiles. I did not explore the acoustic properties of this. Now, what have I done? I have lodged this ping pong ball in this chamber, compressing some air in there. Now I'm going to shoot the ball. And there is an acoustic property that is not so easy to understand. Listen, listen. Up, poop. And I want to know, thank you, sir, I want to do it again. There it is. And I want to know where that sound came from. And that is very difficult. And because it is, I will abandon it here and now. But this all suggests what? That the physics of toys is not trivial. Consider another one. Here is a disc with some holes in it. Some holes. That's good. And the other side is a disc with some holes. So there are two discs, like pie plates, put face to face. And here is a string, and there is a string, and you are, of course, reminded of the toy of the button on the string, the pair of strings. Now I am storing some elastic energy in the wound-up strings. Wound up. And now, listen. And I want to know where the sound comes from. But more important, watch the string. Watch the string now. Watch it. Watch it. Do you see? I'm going to do it again. Uh-huh. Let me show you what was going on the string. Very wonderful thing. Here is the disc here with the holes, and there is a string, and there is a string, and here's what we saw. Here's what we saw. A standing wave on the string, and the standing wave is the behavior of a vibrating string which is resonant to the pitch of the note emitted by this spinning top, or whatever you want to call it. I'm running out of steam there a little bit. So, consider another one of the same equivalent substance. This is two hemispheres put together with holes in them. But you will see they have a different pitch, a different frequency. And again, standing waves on the strings. Now, consider something much more difficult. Here is a little airplane with a string fixed to the nose, and here is a little stick, and the string, which is a piece of nylon string, is fixed around this shaft here. Now, I'm going to hold the string tight and turn the shaft, and you listen, listen. Now I'm going to do as a child would do with the toy. And I will suggest the mechanism. The string on this little shaft, like the rope, the hawser with which a ship is tied to a bollard at the dock. That's what that looks like, a bollard, rope tied around it. What happens when I turn this? The string grabs and lets go, grabs and lets go, which means that the nose of the plane is pulled so and pulled so and pulled so, quite like a violin bow grabbing the string and letting go, which is how a bow activates a string. Now, here is another such toy, which is in the shape of a bee, And this one has an empty chamber, a little chamber, empty, correction, filled with air. Now, I view this chamber here as an open pipe of certain length, and it has a certain pitch. Certain pitch. Now I'm going to close that pipe with a stopper. It is now a closed pipe of certain length, and it will certainly have a different pitch. Right. And so we could make a comparison between open pipes and closed pipes, say in an organ arrangement. Or, I'm still on acoustic toys. My little bird whistle. Here is a little chamber in which is lodged a piston. Piston. Now the chamber is that long, and the piston could be pulled out the entire length of the chamber. I wanted to discover what change takes place in the pitch of a note when the chamber is heated. Because, as you know, when orchestras play and the musicians get hot and the hall gets hot and the conductor gets hot and the instruments get hot and the people breathing get hot and the whole place is hot, some things happen to the strings and to the winds. The strings get less in tension and their pitch goes down, but the wind instruments have their pitch go up. I wanted to explore that, so what did I do? I am blowing this whistle, holding a lighted candle here, and I nearly ruined my whistle, as you can see. But anyway, for the length that I have available, listen to the change in pitch. Change in pitch with change in length of air column. Marvelous thing, marvelous. Or take this trivial thing, which is quite a little toy. Various lengths of slabs of metal fixed at two places in a very special way. Here is a slab of metal fixed right there. Get a view of that right there. This is a xylophone, I suppose. And now when I excite this instrument, here's the way the member vibrates. Its principal mode of vibration And the length and the cross-section determines the pitch of the vibrating member. Some things a little flat there, but the physics is still available to us. Or something quite essentially trivial. Here is a little figure in the shape of a frog, and it has a steel sliver here. And here is another quite like it, but you notice the difference in the sizes of the slivers. There is a wide one, there is a narrow one. Listen now to what emerges when I flex them. Which suggests that the heavier, wider, the one possessed of more inertia, has a lower pitch. So we learn something about the physics of vibrating members by this device. Now, consider a thermal toy, since I suggested I might do something on this program. Here is a little shaft which is geared to a wheel, which turns a disc, and some scraping of a metal is done. And the scraping gives rise to such a high temperature that the metal is made incandescent, and it emits its own light. Watch this. Notice what is happening. I am converting mechanical work to thermal energy. The thermal energy is being commuted to optical energy, or light, a thermal toy. Or another one of the same mechanism. Oh, look at the fire spit out there. No, that isn't fire spitting out. That's a hot little piece of metal. So, question, what kind of metal could we possibly have that gets incandescent with so little work done? So very little work. Another acoustic toy, a pipe. Holes for the fingers. Whoop. I'm not so good a piper, but yet from a study of this we can learn how the length of a pipe affects the pitch. Now, an interesting toy. A chamber with a piston and a little stopper which closes the chamber very tightly. I'm going to close it very tightly, and now push the piston in suddenly. Not only is this a thermal toy, but an acoustic one. Why? When I push the piston in rapidly, it gives rise to compression of the air inside, and the temperature rises very high, quite like the temperature rising in the cylinders in a diesel engine, which you know is fired without any ignition system, just from the high temperature arising from compression. So, this thermal energy, the rise, the elevation in pressure, drives the stopper out. And listen. Now I'm going to take one which is a little longer. Do you see? This one is a little longer. And if pipes behave as pipes should, we will find this pitch a little lower. So, and finally, what we call this, what do you call this thing? An accordion. Yeah, an accordion. I'll not discuss the physics of it. It's a little too elaborate for the time I have here, but I have little levers which can open and close certain orifices, and watch me. Now, I wish I had about an hour to discuss how it is that the sound emerges at different frequencies, at different pitches, or more of the same, which I enjoy very much. Little chambers, which have little diaphragms in them, and holes here, and I turn this one upside down, and I turn that one upside down, and I turn this one upside down, and now I turn them right side up. And we ask, where do the different pitches or frequencies emerge? And it all has to do with the length of singing pipes. So, finally, what have I? Physics of toys, acoustic, thermal. Acoustic, thermal. Let me see. Oh, here is a good one. Here is a good one. A little chamber, a little hole in the chamber, a pipe to blow, and a little spin wheel. What am I going to do? I'm going to use some air from my lungs, drive the air in there. It comes out a little hole. Since this is a vibrating chamber, there will be some music, but the energy also of the emerging air will turn the pedal, the spin wheel. Watch it. And the physics of this would take me a half an hour to explore, and I thank you for watching. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business, and more especially this hour, the physics of toys again, with which we have fun abundant. Now, I call to your attention. I have done some things with mechanical toys, some things with acoustic toys, some with thermally excited, energized toys, now some electrostatic toys. A wonderful thing to witness. Here is a little box made of clear lucite on the top with a cardboard bottom. And in the box I have lodged some little figures in the shape of human figures made of paper. Now what am I going to do? I'm going to stroke the top of this box ever so briskly but lightly with the flesh of my hand and watch. Ah, there they are. There they are. Dancing devils. Now, some are sticking here, and I want to know why they do that. Look at those little rascals. Look at that. Here is one of the same substance, really. Oh, look at that. Now watch. I'm going to put my finger on the upper surface here, and this little rascal down there can do many things. He can drop down, sort of dead, or he can flip away to another place on the underside of the cover. Watch. Oh, well, oh, there, that one did it. Let me show it to you again. Watch. Oh, that one went around. And the exploration of this would take a good half hour. An electrostatic toy. Let's look at a magnetic toy. Here is an iron framework. Iron, it has to be magnetizable stuff. It could be iron, nickel, or cobalt. Question, could it be stainless steel? Answer, no, stainless steel is not magnetic, which is a very interesting thing. And here is a little lucite wheel, which has an axle, and the axle is conical shaped on the very end. Conical shaped, quite like this. So somebody says, what are you making so much of this, Professor? Well, that's it, conical shaped. Why? The physics quite profound. Now what do? I lay the wheel on there. Now what I'm going to do is the following. I'm going to put this into motion mechanically. Down, up, down, up. Now I am in resonance with the moving of the wheel. Up, down, up, down, up, down, up, down, up, down, up, down, not quite. Not quite. Now, the beautiful thing about this is this. Here is an open end, and the wheel is held there magnetically at that open end. Very amazing problem, because the magnetic force must be enough not only to hold the weight of the wheel, but to provide the centripetal force necessary to bring it around and up the track again. Or consider this magnetic toy. Here is one that is absolutely a killer to contemplate. Here is a little hollow sphere which is loaded in the bottom with a little magnet, and you notice that mechanically it's very stable because it has a very low center of gravity. Now here is a little dog. The dog is called der Wunderhund, the wonder dog. A red one, a white one, a black one. Now as I approach the sphere with the dog, an interesting thing happens. Watch it. Watch it. Notice it spins. Let me approach another sphere with another dog. Notice this one goes away. The first one came toward me. Question, what's going on here? Well, I discovered what's going on by breaking away the front feet of the dog, and I found lodged in the front feet a little magnet. And the question is, how must this magnet and how must the magnet in there be polarized in order for these to do what they do? And in order to study that, here's what I did. I took a ping pong ball, cut it in two, put a little tacky wax in the ping pong half ball, and then a little iron sliver, which I magnetized in a very special way. And you watch. I'm afraid it may be too rough here, but watch. Yeah, get a little turning. And so I have explored it in this way in order to suggest to you how a study would be made of something you don't understand. Electrostatic, magnetic. Let me do something else. Consider the following. Let me go back to acoustics. A musical top. Here it has a spirally turned shaft, which obviously fits in a spirally turned cylinder, and when I push it down, the mechanical forces put the top in motion, and I want you to hear the wonderful music which emerges. Listen now. Listen. Isn't that wonderful? Isn't that wonderful? And I ask, how does this make such music? How do these various chords emerge? What is vibrating? I put that question for this reason. In order to have a sound, there must be some vibrating system. And I ask, the beauty in a musical top. A mechanical toy of another sort. Here is a pipe plate. Pipe plate has a lip on the bottom, ordinary. I put a stick in this corner here, and I spin it so. I say that in this position, the moment of inertia of the pipe plate with respect to this axis of rotation is very large. I give it some spin energy, which I would call in physics 1/2 I omega squared. The I being the moment of inertia and the omega the angular velocity. Now what do? I slip the stick into the middle of the disc, and a wonderful thing happens. Watch it. Whoop. Fellow can lose his professional dignity here. There it is. And the wonderful thing is this, that however I incline the axis, the shaft, the disc remains in motion in the same original horizontal plane. Look at that. And notice how long the spin life, because I have given it an enormous amount of kinetic energy of rotation. One more. Wonderful thing. Classic. A little chamber, empty. No, not empty. Filled with air. I put on a pumping mechanism, and I pump it up. Now I have a question to ask, which many fall down on. Consider this to be a rocket, and supposing I have some stuff in here, as I like to say, in a state of combustication. Oh, somebody says, now, Professor, you know there's no such word. Well, if I want a word, I make it. I don't like combustion. It's too quiet. I have some stuff in a state of combustication. The gases from this combustication emerge. I ask, don't the gases coming out here need the air to push against for this to go? And many people think that is so. And then I say, let us pray, because that is all wrong. This thing works best where there is nothing, because we want the gases coming out there to have the mostest stuff and the largest velocity in order to have the greatest change of momentum. So, don't ever think that the gases coming out here need the air to push against for this to go. Now I pump this up. I am putting more and more molecules of air into this chamber. I remove the pump mechanism. The gases come out this way, and this vehicle goes the other way, and I'll ask my man out here, my man Friday, to catch it. There it is. The vehicle went. Question. This is properly designed to put some water into. Question. How much water and how much air should you put in order to have the maximum efficiency? And this is a very difficult mathematical problem to engage in. Next problem, toys, mechanical. I have here a little toy duck on a string. See, there's a duck on a string, so I call it a toy duck on a string. And now you have to get a long shot of this because I want the whole thing seen. And here's what I'm going to ask. Let me hold the upper string at one position. See, it's fixed on the top of my head. And I'm going to pull down on the lower. Watch it. Pull down. I pulled down and the duck went up. Now I'm going to hold the lower hand fixed on the table and I'm going to pull up. Watch. Well, now what is going on? Can I pull the duck up by pulling down, or do I pull the duck up by pulling up? In short, I want to know, what is the mechanism inside this toy duck that makes him do what he does? Or consider the classical business of the dunking duck. That is hardly ever understood, but I'm going to try to explain it quickly. Why does he do what he does? Answer. He has along inside his middle shaft a tube. He has some volatile liquid in his belly. I have wetted his head here in this glass of water. Now there is evaporation from his head. Evaporation is a cooling process, whereupon the vapor from inside his belly, which has come up into his head, condenses in this cool region into the liquid state, makes his head heavy, and down he goes. But when he gets down, the liquid runs back to his lower part, whereupon he is lifted up again. And this is the mechanism by which he works. Finally, the case of, and I'll have to step out here to do this, I guess, the case of the spheres on the strings. 2 rubber balls on 2 strings, and I trust that for you there, you have one going clockwise. Now watch it. There we are, and the other one is going counterclockwise. And I say that in order for this to be done, my hand must execute simple harmonic motion while the spheres themselves execute uniform circular motion. And thus I have mentioned the physics of the two balls on the strings. And I thank you for watching. How do you do, ladies and gentlemen, and boys and girls, and teachers and people? I'm Julius Sumner Miller, and physics is my business. And our special business today, and for several days to come, will be on the subject of waves and sound. And this first program, this first lesson, more deliberately, on kinds of waves and their fundamental properties. Now, by way of preamble, if I were to put the question, what is a wave? You would find it very difficult to answer, because some simple questions are very difficult to answer, like what is a tree or what is a hole, which a child once answered this way: a hole is to dig, which I think is terrific. So we best tell what a wave is by showing different kinds of waves. And this view we call in physics the operational. I can't very well tell you what a wave is without writing some formidable mathematics, which may indeed only obscure the matter. But if I show you some different kinds of waves, you will get a feeling for what a wave is. Now, we characterize waves generally into transverse waves and longitudinal, also called compressional, for a reason you will see. Now let me show you a transverse wave. I have laid out in front of us here a rubber tube. I'm going to take this one first. There are two, in fact. Here is a rubber tube which is so long, under such tension, and so fat. We speak of the linear density. Remember, the strings on a piano, some are long and skinny and some are short and fat. So, this string is fixed at that end, it's fixed at this end, it has a certain tension, a certain linear density. I'm going to give rise to a pulse in it by depressing a part of that tube. And watch. Something went down and something came back. The wave propagation delivered only energy. Nothing of this tube went anywhere except up and down, as I shall show you a little later. So the velocity of this transverse wave, where the particle disturbance is this way and the energy propagation this way, had a certain velocity. Now I'm going to increase the tension, and I'm going to create a pulse again. Watch it. Oh, much faster, much faster. Now I'm trying to get in a place where we can see it better with respect to the table. Now I've increased the tension, pulling it very tightly. Oh, very fast, very fast. Now even tighter still, very tight. Oh, enormously fast. Now that tube is, as I often say, empty, but it isn't, it's filled with air. Now I have another beside it, which is filled with sand. This one is filled with sand. So its linear density is vastly greater. Now, if I had all of the properties the same as in the first one, and I give rise to a pulse, it moves with less velocity, but higher tension, higher velocity. So I have demonstrated a transverse wave, and I will write for you the velocity with which a transverse wave moves. It is given by the square root of the tension divided by the linear density. That is how fat it is. Now, that is a transverse wave. Indeed, all waves answer this certain property. Their velocity is governed by an elastic property divided by an inertia property. And this will become clearer with further demonstrations. So this was a transverse wave. Now, the next kind, longitudinal, also called compressional. Compressional. Let me show you why it is compressional. Remember, in the case of the transverse, the particle disturbance was up and down, and the energy propagation at right angles to it. Now I have a spring, often called commercially a slinky. It is so fat, wound so tightly, under certain tension, I'm going to give rise to a pulse by squeezing some up, storing some energy, and letting it go. Watch now. A compressional pulse went down. I'll make it more deliberate. Oh, not only did a compressional pulse go down, but some was reflected. There it is. The reflection, indeed, we will liken in a short time to an echo. Now, the sound business we have to deal with are compressional or longitudinal waves. Longitudinal waves. And the velocity of sound in air is given by the square root of P over D, where P is the pressure of the atmosphere and D the density. And I hope you see that that pressure business may be likened to an elastic factor and the density business to an inertia factor. Now, there are other kinds of waves, torsional waves. Let me illustrate what a torsion is. Here is a piece of chalk. I hold the upper end firmly, and I twist the lower end. Yes, and if one looked closely, the way this was sheared, this suggests very clearly that a torsional wave advanced along the rod. Yes, let's get that again. The camera got that very well. Yeah, notice how, where is it? You see it is sheared in a twisting way. Now, regarding the velocity of sound, an illustrative matter. Here I have an array of steel spheres on a track. They are highly elastic. I take one up the plane, allow it to collide with the system, and watch how quickly this one feels the impact of that one. Right away. Now we are to view that as the advance of a compressional wave, because that steel ball may be viewed as having a little spring inside which suffers some compression, and that compression runs away. Notice we have a little diversion. A compressor has suddenly gone on, but that's no hurt. You hear a sound, a compressional wave is reaching my ear and the microphone, so nothing to be worried about. What I wanted to say here is this. How fast does this compressional wave advance here? Well, the compressional wave that emerges from my mouth is traveling at about 1,000 feet per second. Here in steel, this compressional wave, 15,000 feet per second. So if this were a foot long, I'll make it a foot long. If that were a foot long, this one would feel that one in 1/15,000th of a second. So we have transverse waves where the particle disturbance is at right angles to the energy propagation, and a compressional or longitudinal wave where the particle disturbance is in the direction of the energy propagation. And we will see later that transverse waves can be polarized. Imagine that rubber tube whose end is fixed over there and I have the free end, and I do this to it. You know, a wave advances down the tube like this. Yes, down the tube. And if I had a picket fence with a slot like this, or a slit, you can see that that wave could go through there. But if I had it turned like this, it could not get through. And thus we discover that transverse waves can be polarized, But longitudinal or compressional ones cannot. So sound cannot be polarized. But sound waves suffer all the other properties of waves. They can be reflected, that's why we get an echo. They can be refracted, that's why you can hear a band around the corner of a building. They can be absorbed, sure, if there were an audience out here, the clothes and the hair and the whatnot, the seats that are all plushed and fancy, would absorb the energy. Now, water waves, another kind of a wave. Very troublesome thing, because water waves are a mess. But I want to show you a water wave and write some mathematics, because it is very enchanting. Here is a tank of water. I am going to drop a little body in this tank of water, and a little disturbance will result, which goes down the trough. Well, it isn't too large an amplitude, so I'm going to make a bigger one. Watch it. There is a wave. There is a wave. And I'm going to write for you the velocity with which water waves move. And for this purpose, I draw from my notes, because I have a secret to tell you. I do not ever bother to remember formulas. Indeed, I let my students take examinations with all the formulas from all the books in all the languages of the world written on them, because memory has not much virtue in my business. It is what we understand that counts. So I emphasize this. Knowing something is quite inadequate. What you must do is understand it. So here is the velocity with which a water wave moves. And notice how much troublesome. G lambda, where lambda is the wavelength, over 2 pi plus 2 pi t over lambda rho. Now somebody says, oh my God, Professor, that's gibberish. No, no, no. No. If the waves are very small, certain things apply. If the waves are very large, other things apply. This tells us the velocity of the propagation of water waves. Now, wave, pulses. Consider the following. Let there be an automobile engine here. Remember, imagination is a necessary ingredient. And I hear a knock in the engine. Something trouble. I want to locate it. What would I do? Well, I could take a rubber tube and put one end there and the other end to my ear, but that wouldn't reveal very much, because wave conduction in a rubber tube is very bad. Let me put a metal rod. There's the trouble over there, I think. I put it there. Club, 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 club. I hear it very distinctly. Conduction along metal is very good, a compressional wave. And that is why, of course, this kind of an instrument works. A stethoscope. Oh, yes, I hear me quite clearly. I am alive. Yeah, that's a very, very important thing. Now, I have spoken of propagation of a compressional pulse in steel, propagation of a compressional pulse in a rod. Consider, sound being a compressional wave mechanism needs something to compress. And therefore, we would show that sound cannot be propagated in empty space. That's why people on the moon could not talk with each other. For this purpose, I could have a bell in a vessel, take out the air more and more and more with a pump, pumping out the air, and I would hear the bell less and less distinctly, which means what? Compressional waves, longitudinal waves, need a medium for propagation. Transverse waves go best where there is nothing, and that's why we have radiation, say, from distant suns, stars, and the like. So I have made clear, I trust, the fundamental distinction between transverse waves and longitudinal waves, about which this series now is engaged. Sound, longitudinal or compressional wave mechanism. And I shall see you again. How do you do, ladies and gentlemen, and boys and girls and teachers? I'm Julius Sumner Miller, and physics is my business. And our special business today is more on sound waves, and more deliberately on these two matters: frequency and pitch. When we speak of a sound, we ascribe to it a certain pitch. A, B, C, D, E, G. A, for example. If I strike A, let me do that. Here I have a bar, which I'm going to strike. That bar has a certain mechanical motion so fast, we call it the frequency. It gives rise acoustically in my ear to my brain a property called the pitch. For example, I struck a bar which vibrates 440 vibrations per second, and we call that A. We call that A. If I struck a tuning fork, let me find one here. I will strike a tuning fork quite like so. That is vibrating 256 vibrations per second, and we call that middle C. So, the mechanical behavior of a vibrating system, we call its frequency, and what emerges acoustically, we call the pitch. Let me illustrate. Here is a metal, oh, and by the way, it needs to be remembered, and very clearly, that in order to have a sound, we must have a vibrating system. And for sound energy to be propagated, there must be a medium for it. Because remember, sound waves are compressional waves, and there has to be something to compress. So here is a piece of steel plate. I'm going to flex it. Listen. It has a certain frequency. It's giving rise to certain pressure pulses that advance upon the microphone and upon my ear. I spoke of pressure pulses. I want you all to try this adventure. It is quite remarkable. Hold your arm in this matter and do some talking firmly on the arm. I say that I feel the changes in pressure on my arm, which emerge from the pressure pulses coming out here, a result of the behavior of my lungs, and the voice that I have is governed by the frequency of my vocal cords, how my mouth is shaped, the position of my lips, where my tongue is, and whether I have teeth or not. A very important thing. Here is another sheet of stuff, a bigger sheet, bigger, more inertia, likely to have a lower pitch. Yes, it does. And here is a bigger sheet of the steel, the like of which I had in the first place. Bigger, more inertia, lower pitch. Lower pitch. Let me speak more of that frequency and pitch business. Here I have some metal discs, which are notched. This one, I hope you see, has 4 notches. That one, 8 notches. That one, 16 notches. And this one, 32 notches. Now, if I put this shaft in a rotating motor and spun it, and held a card or a flexible piece of steel against this one, I would get for each revolution 4 pulses to the ear. This one would give me 8 pulses, this 16 and this 32. Hence, although they have the same angular velocity, they have different frequencies of pulses reaching my ear, and therefore different pitches. Let me show you that here. I have a disc with some holes in it. And I call your attention very especially to the following. The outermost row of holes has the mostest holes. The inner, the next inner, less holes, less holes, less holes still. All these 4 rows have their holes symmetrically separated. The innermost row of holes has its holes unsymmetric. So, if you give me your attention, I am going to try to show you the difference between music and noise. Now, I'm going to have some difficulty with that because for some, boogie-woogie is music, but for some of us, it is not music. Watch me. I'm going to rotate this at a certain speed and drive a stream of air through successive rows of holes. Watch this now. Watch this. Watch. Now I'm going to go faster. Now I'm going to go faster still on the outermost row of holes. Watch it. So you see, the higher the frequency, the higher the pitch. Now all of these emitted pressure pulses were pleasant sort of to the ear. We call that music. Not only that, but the frequencies can be written in a simple mathematical way. Now I'm going to proceed from the outermost to the very innermost, and there the lack of symmetry will tell us something about the difference between sound, music and noise. Now, watch it. Watch now. Watch. I don't think we could classify that innermost one as music. More on vibration frequency. Notice, a meter stick. A meter stick, I fix it to the table so, with such a length hanging over. Very high frequency, very high pitch. Lower pitch. Lower pitch. Lower pitch. Lower pitch still. So I have tried to connect for you pitch and frequency. Consider this, which Galileo observed. Here is a silver coin, a $50. It is milled on the edge. I hope you know why it is milled on the edge. I'm going to run my thumbnail over it, doing exactly what Galileo did in the 16th century. Listen. Now I'm going to take a silver dollar, and I think we'll have a different pitch. Why? The milling is at a different rate, and the inertia of this is of a different sort. Listen. Let me take a quarter, a dime. Remember, something is vibrating. Or just tearing a piece of cloth. Here is a piece of cloth. Listen. Vibrating system. Here is something else that I'm going to tear. Different pitch. Or consider a board which I rasp with a large file. Listen. Certain pitch. Finer file. Higher pitch. Very clearly that. Very clearly. Or take a deck of cards. Listen. Listen. Or a larger deck. Larger inertia, more mass, lower pitch. Now, more of the same. You remember the flexible steel plate, the flexible brass plate. Larger. Now, question. Here is a plate. Listen carefully. Listen. 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 I hear nothing. Somebody says, it ain't vibrating, Professor. Oh, it is vibrating, but at such a very low frequency that it is below the audibility of the human ear, which leads me to remark that the human ear range goes from about 16 vibrations per second to about 16,000. Some say 20 to 20,000. Now, the vibration frequency of this lead plate was so very low. Now, consider, again, the tuning fork business. Did I not say that if I strike a fork, it has a certain frequency, therefore it emits a certain pitch? Later in this series, I will show you a wonderful thing. Here is that bar that I have already struck and made sing. And you'll notice that bar is fixed here and fixed there. These are positions of rest in the bar, and they are called nodes. And the bar is really doing something like that, which I will show you in another lesson. Now, how about a tuning fork? Well, a tuning fork is a bar. There is the bar. And the tuning fork was bent up so that these two nodes are very close together, and a handle was put on. And thus is the mechanism of a vibrating bar. More on the same, but of a different complexion. An enchanting little business that is essentially a toy, but which can be made to emit music. Here is a prismatic rod, rectangular rod, which is notched. And you see that if I run this the stick across the notches, it goes into that hole and up, into that hole and up. Here is a little propeller on the end. Watch the behavior of the propeller. The propeller has a frequency governed by the frequency of the notches on the stick. Mark you, too, this rotated this way when I stroked it here. Now watch it. Aha, aha. And in another lesson, I will talk about compounded harmonic motions which give rise to some beautiful things.